In this video, we'll be looking at polynomial functions, so what they are and how to recognize them. And we will start talking about some terminology related to polynomial functions. So first of all, polynomial functions are made up of one or more terms that are attached by addition or subtraction or multiplication, but the exponents on the variables have to be integers, so that means positive whole numbers. So I have a few examples of functions or relations here. We're going to start off by just circling the polynomial functions. So the first one is a polynomial function. I have the x4, I have the x squared. The second one, I see an x squared and an x term. However, these terms are in the denominator of this fraction, which means if we were to bring these terms up into the numerator, they would have a negative exponent, which is no good. That was actually a rational function there. In the next one, again, I see an x to the power 4, I see an x term, but there's a square root around it, and a square root actually means a rational exponent. So a square root is an exponent of a half, if you remember that from grade 11 functions. The next one, negative exponents, no thank you. The next one, yes, this is a polynomial function. All of the exponents are positive whole numbers. The next one is also a polynomial function. Here I have the brackets attached by multiplication, but if I were to expand and simplify, it would get it into that standard form where the exponents would still be positive whole numbers. Same with the next one. I have exponents outside the bracket, but they are positive whole numbers. The next one, no, because it's a cube root. A cube root would mean a exponent of a third. The next one, we have that negative exponent outside the second bracket. That bracket would go into the denominator, making it a rational function instead of a polynomial. This is a rational function. The next one is a polynomial. All of the exponents are integers. And the last one, the square root, means it's not a polynomial. Now, once a function is a polynomial, we can start talking about the degree of the polynomial. And we can determine the degree of a polynomial function if it's in standard form or if it's in factored form. When it's in standard form, we don't see any brackets or any multiplication. It's just the terms attached by addition or subtraction. And we just look at the highest exponent. So if you look at my example that I've just underlined, I see one term that is x to the power 4, one that's x to the 6, one that's x or just x to the power of 1. This has the highest exponent, the x to the power of 6. I couldn't care less what the coefficient is. I care about the exponent. So the degree is 6, okay? In factored form, you'd have to think long term. If I were to expand and simplify this, what would that highest exponent be? And the shortcut is just add the sum of the exponents on each factor, assuming that each factor is linear. If it's not, you might want to think a little bit about the power law for exponents. But if we look at this example here, I have an exponent of 3, I have the invisible exponent of 1 on the second bracket, and an exponent of 4. So now I can just add these exponents. So 3 plus 1 is 4, plus another 4 is 8. Now that coefficient out front, the 3, if it had a variable attached to it, like if it were 3x, I'd have another exponent to add on. Okay, now I'm just going to go up to the polynomials that we circled in this box, and I'm going to write the degree of each function. So the first one on the top left, it's in standard form. The highest exponent I see is 4 from 5x to the power of 4. So the degree is 4. We call this a quartic function. The next one here, I see that exponent of 7. So this is a degree of 7. This doesn't have a special name. This is just a polynomial. The next one I know I'm going to add the exponents on the outsides here, but you also have to look inside the brackets. The first bracket is quadratic, the second bracket is cubic. So if you think about expanding this out, when I multiply an x squared by an x cubed, that would become x to the power of 5. So this is a degree of 5. This one is partially factored form. The next one we have factored form here. We have 3, 2, and invisible 1. If we add those up, the degree is 6. And finally, the last one, we have this term out front that has an x. X is technically to the power of 1, so we're adding the 1, the 2, and the 5 to get a degree of 8. So knowing the degree of a polynomial is really important because it's going to actually give us an understanding about the overall look of that polynomial and about its end behaviors, and these are things that we will look at throughout this unit. So the next thing I want to look at is just how to classify different polynomials. Now, I have first a little visual here. We have a linear function. A linear function has a degree of 1, something that you saw in grade 9 a lot. Quadratic has a degree of 2. Cubic has a degree of 3. Quartic has a degree of 4. Anything after that is just a polynomial. Now, something I just want you to look at and observe, and we'll go in more detail on this in another lesson, is that 2 of these functions have an odd degree, so the linear and the cubic, and the other 2 have an even degree, the quadratic and the quartic. If you look at the linear and the cubic functions, you'll notice that if I look to the left and to the right, they're going in opposite directions. So for the linear one, it's going down into the negatives forever on the left side and going up to the positives forever on the right. And the same thing is happening with the cubic, down forever on the left and up forever on the right. Whereas with our quadratic and quartic, it's going in the same direction long term on the left and the right. That's actually going to be very helpful for graphing purposes later on. So I just wanted to bring that to your attention right now. Now, we can classify a polynomial just by looking at it. We could have a general idea of what kind of function it is, and once we get into graphing, we'll get a better idea of that. But from a table of values, we can use something called finite differences. Now, in grade 9, when you were learning about linear functions, you saw that if you had a table of values and you calculated the first differences, it was the same value. And first differences are just when you take the y values and subtract bottom minus top, the consecutive y values. For a quadratic in grade 10, you learned that the second differences were the same, and you can actually apply that to all polynomials. A cubic function, which has a degree of 3, will have constant third differences. A quartic, which has a degree of 4, have constant fourth differences, and the pattern goes on. So I just have a random polynomial function here, and I want us to classify what kind of polynomial it is. So I'm going to start off with my first differences, and I'm just going to pair up. I start from the bottom, and I'm going to do negative 16 subtract negative 9. So negative 7. Negative 9 subtract 4, negative 13. 4 minus 11, negative 7. 11 minus 0 is 11, and 0 minus negative 41 is 41. I'm not sure why I put a negative in front of the 0. That's just a typo there. My apologies. Okay, these are obviously not the same values, so it's not linear. So I'm going to go to my second differences, and here I'm going to take my first differences and pair those up. So negative 7 subtract negative 13 is 6. Negative 13 subtract negative 7 is negative 6. Negative 7 minus 11 is negative 18, and 11 minus 41 is negative 30. These are not the same number. It's not quadratic, So I'm going to go to my third differences. 6 subtract negative 6 is 12. Negative 6 subtract negative 18 is also 12. And negative 18 subtract negative 30 is also 12. The third differences are constant. So this is a cubic function or a polynomial with the degree of 3. And actually, just a little fun fact here. After you figure out which finite difference is constant, we can actually figure out what the leading coefficient of the polynomial is. So we know the function is going to be y equals something x cubed, and then it continues on, maybe an x squared term, maybe an x, maybe a constant. It goes on, but we can figure out this value here, which is the a value, the leading coefficient. And the way we do that is this value here that was constant, that 12, is equal to the value of the leading coefficient times whatever the degree of your polynomial is. So the degree of the polynomial is 3. We found that from the finite differences. Factorial. What factorial means, if you've never seen it before, it just means take 3 and multiply it by every integer less than it. So that would mean 3 times 2 times 1. And you actually do have a factorial button on your calculator. So 3 factorial is just 6. So that means that's 6a. So the a value must actually be 2. So the equation of this cubic function is going to start off as 2x cubed and then the rest of it, okay? Which you actually can solve for if you really wanted to. We have a lot of coordinates on this function. You could do some substitution elimination by subbing some points in and getting a few equations. We're not going to do that, but just I wanted to show you this little extra piece here in case you found it interesting. But that's kind of it for this mini lesson. Like I said, it's just showing us a bit of a classification of polynomials and how to look at equations to know if something is a polynomial or not. And we've introduced that degree terminology, very briefly looked at some end behaviors or how a function looks long term to the left and the right.